This video will focus on the learning target. I can determine the overall polarity of a molecule and use proper symbolization to represent the polarity. So far we've already talked about bond polarity, and that's the idea that as two elements come up and are either sharing or transferring electrons, depending on the electronegativity or the pull of the positive nucleus on those bonded electrons, determines what will happen to the electrons. So either neither will pull very strongly and you'll have a nonpolar bond, or one element will pull more strongly and you'll have a polar bond, or one element will pull so greatly you'll have an ionic bond. So essentially that term polar, again, is the fact that there's an unequal distribution of the charge then. Okay, if they're equally sharing, then it's nonpolar. But if I end up having one pull more strongly than the other, then you'll have this area of positivity and an area of negativity. An area that's negative is the side where the electrons are tending to hang out more, and the area that's positive is the side where the electrons are hanging out less. So the pictures down here show it again in a polar covalent, because in this example, chlorine is tending to pull the electrons towards itself more than hydrogen. I end up having electrons, right, more on this side than they are on the other side. What that creates are these partial charges, right, these dipole moments where I have a partial negative where the electrons are getting pulled to, and a partial positive where the electrons are getting pulled away from. Okay. So I'm drawing in here as a dipole moment arrow, the idea that you're pointing towards where the electrons are being pulled to and then leaving behind the area that's slightly positive. Once I have a full transfer of electrons, like in an ionic bond, I no longer have partial charges, I have full point charges, right? Full positive, full negative, right? So that's the difference in charge. And charge really is a really important concept in chemistry, because the electrostatic force of attraction is what's dictating essentially all of the interactions, right? It determines what type of bond there is, it determines how close electrons are, eventually it'll determine how things react. So again, that partially negative charge is written with that partial, and then the partial positive is written with the partial. So when we think about molecules then, the fact that I have more than just one bond, but I have multiple bonds within my structure, we can ask the question, well, which molecules end up being polar? Okay, is it any two atoms that have a polar bond? Do they have to have a polar bond? You know, what are basically the requirements of molecular polarity? Overall, what I'd like you to remember from molecular polarity is we have to have an area where the electrons are hanging out. So some kind of area of difference, something that would account for the idea that things are happening that is different in one spot than another, which will give you a pooling of electrons. So essentially, I think of polarity sometimes as like a pool of where the electrons are kind of hanging out. That's a P, can you tell? So, which molecules are polar and which ones are nonpolar? Well, step one, you need to look in your structure and determine what types of bonds you have. So for example, if we look at this carbon dioxide, right, this is CO2. The first thing I would have to do is look at my two elements that are bonded, and then for each of these bonds, do I have a pull? Is there a potential that I could have an area of difference or a place where electrons are pooling? The way we determine that is by looking at that difference in electronegativity, or I sometimes abbreviate it to the DEN, the difference in electronegativity. So carbon is 2.55 and oxygen is 3.44, which gives us a difference that's greater than that 0.4. So these are definitely polar bonds, okay? There's definitely a pull. If I put these pulls on there, I would be pulling from the carbon out to the oxygen and from the carbon out to the oxygen, right? Both are polar, both are pulling. So I'd have my area of negativity pulling that way and my area of negativity pulling that way. Now the problem is, to have an overall molecular polarity, I have to have an area of difference, a place where electrons are pooling. In this particular example of carbon dioxide, I have this happening, right? two sides pulling, and they're pulling equal and opposite. And so if they're pulling equal and opposite, no one wins. I don't end up with electrons pooling anywhere. And so this whole structure is considered nonpolar. It has polar bonds. They're not pulling equally, but because the geometry cancels out their pulls, they're equal and opposite, that's considered nonpolar. Over here then instead, if you start out looking at the bonds, determine if they're polar or nonpolar. My carbon-hydrogen bond is considered nonpolar because the difference in electronegativity is so small. It's less than 0.4, so that's nonpolar. Carbon and oxygen, though, is big enough, just like over here, that it is polar, which means I'm pulling this way toward my oxygen, creating that area of negativity on this side, leaving behind a positive over here. In this case, the areas aren't being canceled out. There's no dipole over here that's canceling out my pull, meaning this one is polar, right? I have a pooling of electrons happening over on this side and leaving kind of a vacancy of electrons on the other side. So the short story, in my opinion, is that if it's symmetrical, it's going to be nonpolar because you're not going to pull in any one direction. Nothing wins. Non-symmetrical things then tend to be polar. Okay, so now there's certain things you can look for if you want to help you determine if something's polar or nonpolar. Step one, when we're going to look at the central atom, okay? And if the central atom of a molecule has electrons, it is always going to be polar, even if the bonds are nonpolar. So this is so nice. I love in chemistry when I can hang my hat on any kind of always. So always, if your central element has electrons or valence electrons, then it will be polar. Now, this structure I have on the screen right here is an example that does not fit this, right? My central element does not have any electrons. My outer elements do, but the center does not. So that is not a good example. Now, the other thing I can look for is just a molecule with any area of difference. So if there's different atoms bonded to the outside, it's going to be polar. Now, if the central atom has these atoms all bonded to it and all the atoms are the same, it's going to tend to be nonpolar even if the bonds are polar, okay? And then if you have all nonpolar bonds, it's going to be nonpolar as long as you don't have any unshared electrons in the center. Now, this case I do have boxed over here as a special note. When I draw the Lewis dot of these four bonded objects, it looks like it could be nonpolar, right? It looks like I can arrange the bonds so that in the end, I'm pulling everything equal and opposite, in which case all of the bonds should, all the bond pulls should cancel out. So I show you the three-dimensional object up here to help you understand what it actually looks like. So in reality, in three-dimensional space, those four bonds don't arrange in a flat way. They arrange like three-dimensionally. So there's no way to get those bonds across from each other. So here's some more application to help you understand the rules. Okay, in each of these cases, so for step one up there, I look at the center and I see there's no electrons in the center. So no electrons in the center means I have to keep going. So I'm gonna ask myself the next question. Is everything bonded to the center the same? And when I look at that carbon dioxide, I go, yeah, all the things bonded to carbon dioxide are the same. And so since that's the case and it's very symmetrical, that carbon dioxide is nonpolar. Okay, this one's nonpolar. Now this example here, formaldehyde, oh sorry, that's not formaldehyde. I think it's hydrogen cyanide. The carbon in the center, again, doesn't have any dots on it, so I have to keep going. And when I look at the outside, I see that it has two different things bonded. What that means is it's not symmetrical anymore, and there probably is a pooling of electrons. I'm going to check and make sure the electronegativity difference in these bonds is big enough to create a pull. And if I do that, I see that my carbon-nitrogen, it does pull toward the nitrogen strong enough to create this area of pooling of where the electrons are, and then leaves behind an area where the electrons aren't. So that means this one is polar. For water, which is bent right here, because there are unshared pairs of electrons in the center, always polar. No questions asked, right? I have these dots on the center, automatically polar. Not dots on the outside, dots in the center. Next one, I notice I don't have any dots in the center, so I have to keep going. Okay, I'm gonna look around the outsides. What you can't see here is there's an O right here. So that first one, if I look around the outsides, I see that I have all this same element bonded to it, which means even though there is a pull toward the oxygen, every single oxygen is pulling, which means they're all pulling equal and opposite. So in this tug of war, no one wins. So that's considered nonpolar. There is no area where electrons are pooling. Down here though, instead, again, I still have no electrons in the center, but that oxygen is pulling and the other two are not pulling at all. So that ends up being polar. So if there's no dots in the center, you just have to take it to the next step and look for that area of difference on the outside. This oxygen is my huge area of difference, so it's polar. A couple more examples then, right here, dots in the center, always polar, no questions asked. Next one, no dots in the center, so I have to keep going. If I look around the outside, I see all the hydrogens are the same because there's no area of difference. That means it's nonpolar. Where down here, I see that this fluorine is different than all the rest. If I look at my electronegativity difference, I'm definitely going to pull toward fluorine, which makes that one a polar substance. The other thing you should be able to do, and it's something I've done along the way, is label, if it's polar, where electrons are tending to pool. The electrons will always pool wherever you have the largest electronegativity. So whatever element has the largest electronegativity, that is where your substance will become negative. And essentially the positive is just kind of always on the other side. So nitrogen is my negative one up here, which means the positive is just kind of on the other side. Okay? I can't label poles on my nonpolar thing because nonpolar things don't have poles. Okay. Over here, my oxygen is my most negative, electronegative, so I'm going to label that negative. On the opposite side is where it's positive. For water, oxygen is the most electronegative, which means it's positive just on the other side. And again, for this one, nitrogen was the most electronegative, so it's positive just on the other side. So that's a video running through how you can tell if something's polar or not. Again, polar means that there's an unequal distribution of electrons, meaning some atom within your structure is pulling more than the others. And the way you can determine that for a molecule is by areas of difference. If you have an element around the outside that is different than things in the middle, that will make it polar. And then really these dots in the center is an area of difference. Given the fact that it's not symmetrical around that oxygen in the center, makes it polar. That's it for this video. Go do a couple practice exercises on this to continue the assignment, and have a nice night.